Good afternoon, everyone. This is Dr. Rehab El-Maghraby, your teacher for today, and today will be about practical lab experiments in oil and gas. Through this session, we will talk about lab experiment, how to calculate porosity, how to measure porosity and water, oil saturation, liquid and gas permeability, contact angle and interfacial tension for the session for today. There should be other session where we go through a more advanced lab experiment, such as how to conduct enhanced oil recovery experiment, how to conduct capillary pressure, measure capillary pressure and viscosity, and so on. So it is displayed on the monitor in front of you. So the first lab experiment that we will discuss first is the porosity. How can we measure porosity? First, why porosity is important. The main thing that we measure using the porosity, it gives us an indication about the pore volume of your rock. So you can know the capacity or the storage capacity of your rock. You can use the pore volume to calculate enhanced oil recovery and to calculate the saturations. In general, so what is the pore volume? What is meant by the pore volume? It is the void space occupied by your, the void space occupied can be occupied with oil, gas, and water. Okay, so in the bulk volume of the core. Okay, so for the porosity, a typical oil reservoir will have a porosity ranging from 10 to 25%, and it can go low, but and also can have a high porosity of higher than 40%, up to 40%. In general, we all know that the rock contains pores, but I want you today to see this photos. This is interesting photo about ketone carbonates. You can easily see the carbonates and the pores in this photo of the ketone carbonates type rock. This is just a normal photo, but if we get this ascent section of this ketone carbonates and we look it through through micro-CT scanner, you will get nicely, you can see the pores here. So it's this pores or pore volume was occupied with brine, and you get a image or photo from using micro-CT scanner. You will, at the end, you will get this interesting photo, how you can see how the pore volume here and here and here. So all the blue colored is brine occupying the pore volume, the void space in the core.
Dr. Rehab, I'm so sorry.
Also,
can you just
can see here.
Dr. Rehab?
Yes.
Can you hear
Yes.
me?
Yes.
Yes, your voice is breaking. So can you like shut off your camera
yes.
and then so the all the connection focuses on the voice? Yes. Thank you.
So as you can see here in this photo of ketone carbonate, it is a thin section for all the pore volume in this core was filled with brine, and you can see this is a blue colored area. Okay, and also in this grain, this gray shade is the grain of this ketone carbonate. It is a circular type, and you can see tiny small pores inside this grain. So this ketone carbonate type rock is characterized with a double porosity. So the bigger size pore volume, and inside the grain itself, there is a tiny micro pores, smaller size inside every grain, and you can see it clearly. Okay. So I will show you another photo of ketone carbonate using the scanning electron microscope of the grain and the pores. Also, the black here, the black shades here, is the pores of the rock. Okay, so we now can visually see the pores inside the rock. So can we see how these pores are connected? I find this interesting photo. Done by a group at Imperial College, my supervisor is Model Blonde. So this was ketone carbonate photographed using micro scanning So this was the core. This is the core plug, but it is a tiny core plug. Like the diameter is 0.5 centimeter, and the length is 2 or 3 centimeters. And what they fill it with brine. All the pore volume are filled with brine, and then they go through the micro CT scan, and they removed all the grain. So what you see in this right side photo is the pore volume connected together, how the pores are connected to each other. All the brine was occupying the pore volume, the available for them, or available for the brine. So the interesting about this, how the pores, so this is a pore and this is a neighboring one, and they are connected together using a small bridges. So there is a tiny small bridges connecting this pore volume together. Here, as you can see here, okay, and connecting to the neighboring pore, big pore, okay. So the tiny radius. So this is a pore. Of course, it is a very small, a small diameter, but there is a smaller diameter. So the smaller diameter is called throat. Okay. So we have a pore. The smallest diameter in this pore is the throat. You cannot enter the pore else you pass through this throat. Okay. So to define the pore and the pore in a more easy way, so we can say that the pore is a small tiny pore. Small is like the room that you are sitting in. Okay, and the grains of this pore is the wall of this room. So, and the throat is like the door. So if you your size is enough to fit through this throat or this door, you can enter the room. But if you are trying to make an elephant, even if the size of the room is enough to accommodate this elephant, it cannot go through this room. Okay, so for any gas or for any particle or whatever thing you are going to inject or are going to flow through this pore, it has to be enough size to fit through this throat. To measure the porosity or to get any production from any reservoir, these pores have to be connected together. So as you can see in this photo again, so it is connected together. If the pores of the rock is not connected together, you cannot get any production from this. So as you can see here, so the core is nicely connected together, and the pores are nicely connected together, and you can advance from one pore to the other pore and so on. So you can get a production, okay, and you can measure the porosity. If the pores is not connected together, there is no bridges between them, there is no connection between them, then there is no production, and you have to use another unconventional method. Type the porosity and the total porosity. For the effective porosity, it is just measuring the interconnected pores that I showed you before in this slide. Okay. So the effective porosity is the connect. I hope that the sound is okay. Okay, so the effective porosity is the measure of the pore space of interconnected pores. So if you are standing in this side A, and you want to go through the other side to produce from the other side B, so you have to pass through this. So if the pores are not connected together, you cannot pass from this side to the other side, like the isolated pore here. So the blue one is isolated. You cannot produce from it. This is at the end. You cannot produce from it. So the effect porosity is the interconnected pore, and this is what we are measuring in using helium porosimeter. Okay. For the total porosity, is all the pores is either connected or unconnected, and this is not used. You can measure okay on the lab, but I will not discuss it using, and you cannot measure it using helium porosity. So again, to sum, what is the porosity? The definition of the porosity is the volume or the pore volume available for the water, oil, and gas to occupy divided by the bulk volume of the core. So this is a core sample. So this is the bulk volume of the core sample. There is void space. This void space over the bulk volume is the definition of the porosity. So how can we measure the porosity in the lab? We use helium porometer device. So the helium porometer, mainly we use helium gas. the helium gas, we use generally helium gas because of two reasons. The first thing, the helium gas is inert. It cannot react with the cores, because if the gas reacting with the minerals or grains of the core or the pore, the porosity at the end will increase, would not be an actual porosity. Okay. And the second thing, the helium gas has a very small molecular size. So you remember I told you that to enter to the pore volume, you have to pass through the tiny small throat. Okay, so if the molecule of the helium was tiny and very small, so it will be easy for it to pass through this throat and fill this nicely pore volume. Okay, so we can get accurate measurements for porosity using helium porosity. So for the helium porosimeter here, you have it is composed of two containers. So the first container is a container where you place your core plug in. So you have a core plug. You open this container, place your core plug in, close the container. So this is the hydraulic piston, or it can be manual piston. And you have other containing helium. You fill this container with helium. This is an example of the shape of the helium porosimeter device. There is many versions, many suppliers for helium porosimeter, but it is working in the same principle, using the same principle. So you have a container of a core where you put your core, and inside this mirror there is a container containing helium, and this is the pressure transducer. So this is the pressure transmitter, the container of helium inside this box, and the core container inside this box. And this is the valve that you can vent, or you can expand around from one core to other, from one container to the other. So I told you that we use core plug. Okay, so we put in this container a core plug. What is meant by core plug? So in general, a core plug, you have a big size core. You drill a small, a cylindrical type core, and it is a standard size. So in most experiments, you are using standard type cores. Does all the core plug has to be regular size? You can measure porosity for irregular size rocks, but I will not discuss this here, and it is not the standard lab experiment. The standard lab experiment we use for the saturation, for relative permeability measurement, for whatever permeability measurement, enhanced oil recovery, all what we are using is a standard type core plug. So what is meant by standard type? It has a certain diameter. So the diameter is up to 1.5 inches. So it can be from 1 inch to 1.5 inches. So it is up to 2.8 centimeter, and the length from 3 inch to 2 inch. Okay? So this is a standard core plug. So how can we calculate the plug volume? The bulk volume. So the bulk volume in general of the core contain grain and pores. So the bulk volume of the core is equal to the volume of the grain plus the volume of the pores. But we are using regular shape size, so it is the volume of the cylinder. So pi squared over 4 times the length. So this is how we can calculate this bulk volume. Back again to the helium porosity. So as I told you, there is a plug, core plug placed in this container, and this container is filled by helium. There is a valve connecting both containers together, okay, and this should be closed. What happens here? Once you open, if this is filled, this container is filled with helium. Once you open this valve, the helium will expand through this line and fill the void space in this container. This follows Boyle's law. So it is isothermal gas expansion. So it follows P1 V1 equal P2 V2. In this condition, the initial condition here, while this valve is closed and you fill this container with helium, you can read the pressure. So for the initial condition, this container, helium container, is filled with helium gas, and the pressure can be read. So you read this pressure at this initial condition will be B1. And the volume of this container is known, it is V1, okay? So once you open this valve, the helium will expand. What will happen to the pressure? The pressure will drop. You will leave it until the pressure stabilizes, and you can read this pressure. So the pressure after the expansion will, in this case, will be V2, and V2 is all the volume that is occupied by helium. So this volume will be considered, and this volume will be considered. So if you know, you already know B1, you know V1, and you know B2 because you measured it. If you know V2, so you can calculate this process. But how we can calculate the pore volume? So V2 is equal to the volume of the helium gas container plus the helium expanded to this container. So it is filling all the pink container. So this is filling this volume, the pink one. So the pink one equal to the volume of this container, take away the bulk volume of the core plus the pore volume, because the helium will expand in this pink shaded space and also through the pore volume inside the core. So in this case, after the gas will expand, the helium will occupy the helium gas container, which is V helium, plus the pink container, all the volume. Okay, take away the bulk volume of the core plus the pore volume. Okay, so the pink container take away the bulk volume of the core plus the pore volume. So you know it is given the volume of the helium container, which is V1. The volume of pink container is already also given. The bulk volume of the core you can calculate, and at the end, the only unknown here is the pore volume. So porosity can be calculated through pore volume divided by bulk volume. Bulk volume you calculated, and pore volume you calculate can be calculated from the isothermal expansion using Boyle's law. So to practice this, we have an exercise here. So imagine you have a helium protometer and you have done some measurements. So what you have done is you fill this helium gas container with helium gas, and the pressure, you read the pressure here to be 765 kilopascal. And the volume of the helium gas is known to be 31 centimeter cube, the volume container. So you know the pressure of the helium container at the start, and you know the volume of the helium container. Okay. So you open this valve, and the helium will expand to fill the other container. You know you was given that, or you measured that, the pressure dropped to 230 kilopascal. Also, the volume of the sample container, this container, is known 124 centimeter cube. You also can measure the dimension of this standard core. The diameter of this standard core is 3.5 centimeter and the height was 7 centimeter. Can you calculate the porosity of this sample? It's straightforward. You have the porosity equal the pore volume divided by the bulk volume. So as you can see here, the pore volume divided by bulk volume. So the first step here is to calculate the bulk volume. It's pi d square over 4 times L. So you know the diameter of this core to be 3.5, core plug, 3.5 centimeter, and the length to be 7 centimeter. You can easily calculate the bulk volume. The next step is to calculate the pore volume. If you remember, I gave you one of the equation Boyle's law that follows Boyle's law. So V1 was the initial pressure of the container, helium container. V1 was the volume of the helium container. It's given. So V1 was given. The volume of the helium container is known and given. V2 was measured. You measured it after the expansion of helium is V2, and the volume of the sample container already is known. So using this equation, you can, the only unknown for this both equation is the pore volume. You can try to solve this practices. So you can solve and get the pore volume to be 15.41 centimeter cube. If you divided this pore volume that you obtained, divided over the bulk volume, you will get the porosity to be 22.9%. So the porosity is expressed as a volume fraction. So in this case, volume over volume. So it's a volume fraction can be expressed with a volume percent. The next measurement here that we have is water and oil saturation. sorry. So for water and oil saturation, so do you have, does the pore volume, all the pore volume of the rock is occupied by oil? No, it is not fully filled by oil. It may contain water, oil, and gas. So this is actual photo of brine and supercritical CO2, but I don't want you to be confused with supercritical CO2. It is the same behavior as oil. Oil is analog to supercritical CO2 and nearly the same behavior. Okay, so what you can see here is that the pore space here can be occupied with prime and oil or prime supercritical CO2 as a gas, so they can coexist using inside this pore volume or pore space. But how to calculate the saturation? What's meant by the saturation? It is the fraction of the pore volume that is occupied by the fluid. So if you have whatever fluid that you want to measure the saturation of, so it is the volume of this fluid divided by the pore volume. So if you want to calculate the oil saturation, you will divide the volume of oil divided by the pore volume. Again, for the water saturation, so if you want to know the amount, the volume of this, or the fraction of this blue shaded area, so you will calculate the volume of water in this area divided by all the pore volume. The pore volume is contained blue and white. The brown thing is the grains. The brown shades is the grains. So what about gas saturation? So gas saturation, again, it is the volume of the gas divided by the pore volume. In general, I want to, if you have, so saturation can be ranging from 0 to 1. So if there is no, so if you look at the saturation of oil, so if there is no oil in this pore volume, no void space contain oil, so the volume of oil in this space will be 0, and the pore volume, whatever it will be, whatever number, so the saturation will be 0. Okay, so what is the maximum amount of oil that you can have in the pore volume? It is the total pore volume. All the pore volume can be occupied with oil. Okay, so if imagine this is not an actual case, but imagine that you was able to fill all the pore volume with oil. So in this case, the volume of the oil will be the pore volume. So the saturation will be 1. Okay, so saturation can range from 0 to 1, and it is a fraction or percent. So it's a also volume fraction. The summation of water saturation plus oil saturation plus gas saturation will be 1 in the same pore space. In general, the saturation for oil field may range from 10 to 40% for water saturation. How to measure the amount of oil saturation, the amount of water saturation inside a core plug that was taken from the oil field, okay, or whatever place that you have your core coming from. So we use this called Dennis-Stark distillation apparatus. So Dennis-Stark apparatus are used mainly to measure the water saturation. It is a non-destructive test, so you cannot destroy your core. So your core are not destroyed. If you work correctly, you can use your core again. So once you receive your core plug, you will weight it using a balance. So you have your core plug in your hand and you will weight it. So this is W1. So the weight, can you imagine what is the W1 for? It is the weight of the grains, the weight of the formation water, which contain distilled water and salt, plus the weight of oil. So this is W1. What is what you are measuring is using this balance is W1. The next step is to put your core in this glass container and fill this flask with toluene. So in this case, for Dennis-Stark distillation, we use toluene. So you heat, you fill your flask here with toluene, and you put it in a heating mantle. You heat the solvent up and to the boiling point, and the vapor of the toluene will start to form. So as you can see here, so how this is how the core is placed. It's like the white container. It's like what it's called sample. So so you will place your core here, and the vapor of the toluene go through your pore, through the core and the pores of this core. Okay, so the vapor starts to form, to rise. Some of this vapor will condense and dissolve some of the oil in this core. Remember, the core contain oil, contain water, and contain salt. Okay, so the toluene vapor vaporize, and some of it dissolve the oil inside this core here and go back to the flask. So vaporize, dissolve some of the oil here and go back to the flask. Okay, and some of the others, because it is continuously evaporating, the toluene vapor are continuously coming. Some of this vapor will heat up the water because the boiling point of toluene is higher than the water, so it will cause the water to vaporize. Once the water vaporizes, the vapor of the water and some of the vapor of the toluene will go up through this glass compartment and to the condenser. They will lose some of the heat and will condense back to this graduated type glass. So it is a graduate. So the glass will, the vapor of water and toluene go through this glass and up to the condenser and go. This is a graduated port, graduated glass port. Okay? So you can measure the level of water that you are collecting here. It can be dead end, or you can have it here. So water, you receive water. Some of the toluene also can condense with the water, but there is toluene and water does not mix. So you can easily know the amount of water that is inside the core because you should vaporize all the water in this core plug. Okay. So the vapor of the toluene continue to rise and heat up the water, vaporize together and condense back the water and toluene. If the level of the water increase, the level of the toluene also increase, and some of the toluene will go back here. Okay, dissolve some more oil and back to the flask, and the cycle is closed. So I told you that we have collected here water. All the water in the flask in the core here are collected in this tube that it is cylinder. So we can easily measure the volume, but this water is only distilled water. You didn't vaporize the salt. You just vaporize the water. So this is distilled water, and there should be some correlation that you have to make to account for this salt. Because if you have like 100 milli of distilled water and you add some of the salt to it, like whatever volume of the weight of the salt you will add, so the volume of the water will rise. You will at the end will not have 100 milli, you will have not like for 110, 120 milliliters. So it is a different volume. So because saturation depending on the volume, you have to calculate this volume accurately. So the saturation that you want is the formation water. The formation water is not distilled water. It is water and salt. So it is a salty water. You have to account and do a correlation for this salt. You can, I will not discuss, I am trying to keep this lecture as simple as possible. And there will be, so I will not go in more detail. So for if you want to read more, so you can go and read more in this how to make these correlations. So for the saturation of water, so it's the volume formation, the volume of the formation water that you collected divided by the pore volume. So you now can calculate accurately the water saturation. Okay, so now we calculated the water saturation. So how to get this oil? The oil dissolved with the solvent. So how to calculate it? First, to calculate the oil, we have to clean the core because I told you that there is a formation or formation water, which is brine, salty water. So what we evaporated was the water, and what the solvent dissolved was oil. So there is salt precipitation inside this core, and you have to clean it. And we clean it using sock slit extraction. So in the sock slit extraction, you place your core inside this glass, and you fill the flask with methanol. because methanol is able to dissolve the salt from your core plug. So what happened here is you put your flux, all the setup inside a heating mantle. So you heat the methanol up, the methanol will rise, and then through the sport, and then through the condenser, and the methanol vapor will transfer to liquid drop by drop, dissolving on top of the pore, going through the pore volume, dissolving the oil. So and the level of the methanol started to rise. Okay. Once the level of methanol that dissolved the salt, so it is methanol and salt, dissolved and starting to rise until it reaches the height of the siphon tube, and the siphon tube action starts. All the methanol will be emptied and go back to this flask. What is vaporizing is the methanol, the clean methanol, and repeating the cycle again while the salt is in the flask. It's not vaporizing. So now you cleaned your core, you have a clean core. You have to dry it first. So how we can dry the core? So we dry the core using an oven. It's not a normal oven, it is a vacuum oven. So if you want to dry it, you have to keep the temperature of the core at 80 degrees Celsius, 90 degrees Celsius as a maximum. If you increase this temperature upper than this, you will cause the water to dehydration to the clays, and you will damage your core. You can initiate a reaction inside the minerals of the grains, so you don't want to damage your core. If you want to preserve your core, you don't have to increase the temperature. So why we are using vacuum oven, not a normal oven? Because if you imagine you have a flask filled with water, at atmospheric temperature, the boiling point of the water is 100 degrees Celsius. Okay, so if you decrease the pressure, if you started a vacuum, look, what will happen to the boiling point? The boiling point will decrease. So at the same, so I'm sorry. So what will happen here is the volume of the temperature. I'm sorry. So the boiling point of the water will decrease, will be lower, like 60 degrees Celsius. So instead of being 100 degrees Celsius at a perfect vacuum, the temperature of the water will be like 60 degrees Celsius. Okay. So you now can evaporate any solvent at a lower degree or at a lower temperature, which means that you are preserving your core, not damaging your core. You will keep everything the core plug to cool down, and then you will wait your core plug. Now it is W2. So the weight of W2 is what now? Is the weight of the grain, because it is clean, no water, no oil, no salt inside the core, and it is only the weight of the grains. So if you take away the weight, the first weight that we take once we receive the core was the weight of the grain, weight of the oil, weight of the water, weight of the salt. Okay. Take away this weight that we take of the clean core, it will be only the weight of the grain. So the difference between them will be the weight of the oil plus the weight of the formation water. Remember, we just calculated the volume of the formation water. And if you know the density of the formation water, you can know the weight of the formation water. Take away the weight of the formation water from W1, take away W2, you will get the weight of oil. Okay, so once you get weight of oil divided by the density of oil, you will get the volume of oil. So volume of oil divided by the pore volume, now you can get the saturation of oil, or the oil saturation. Okay, how we measure the density? You can measure the density easily in the lab. You have here a syringe. You fill it with 30 milliliter, so a tiny small sample, 30 milli, 40 milli of oil of formation water, and you inject it through a tube, a U-tube here. It's a called oscillating tube, and through this window you will see that there is the U-tube are completely filled without any air, and you can get an accurate density measurement of up to 4 decimals. So now we calculate the oil saturation. So if there was a gas, but I want to tell you something. The oil saturation that you get from this through this method is not very accurate, because you can, if some of the grains was separated from the core, it will affect the weight because you are depending on the weight. Okay, so you will take this oil saturation as an indication of what is the amount of oil in this core. Okay, but it's not accurate measurement. So for the gas saturation, if there was a gas, you of course you cannot measure the gas here by this way, but we can say that one, take away the oil saturation, take away water saturation, you can get the gas saturation. So this is how we can measure the water and oil saturation in the lab. There is other ways you can measure the saturation, like when we are doing relative permeability and or enhanced oil recovery measurement called CO2 storage measurement. We know that we can calculate the amount of the saturation using different ways. Like for one of the methods, the most advanced method currently are being used using CT scanner. Okay, so and there was other method like the expansion. We know the amount of the water, whatever. So it's there is other method, but as I told you, this is an introductory session, and I will not go in more details. So regarding liquid and gas permeability. So you know that the permeability, in this case, we are talking about how to measure gas and liquid permeability in the laboratory. So permeability is a measure of easy which this fluid, either gas, oil, or water, can move through this porous rock. There are two definitions for permeability. Of course, permeability is very important. You have to plan your field development using the permeability. You cannot produce using conventional method in a unpermeable formation. So you have to use unconventional method. So okay, so knowing the permeability of your core or your oil field is very important. So these two types are actually there is three types of permeability: absolute permeability, effective permeability, and relative permeability. But I will talk only about two types. Absolute permeability is if you have only your core plug that I showed you before. If this core plug contain only one phase, like water only, or oil only, or air only, so it is single phase occupying the pore volume. So in this case, as the flow passing the same phase passing through the core, so the easy with which this fluid or water pass through this core is the absolute permeability. For the effective permeability, in this case, it's not one phase. It is two or three phases are occupying the pore volume. For the core plug I told you about, if inside this pore volume there was oil and water, and you are flowing water through it, this is the relative permeability. So how this water can flow while there is water and oil inside this core occupying this pore volume. Maybe there was also not oil and water only. They may be three phases like water, oil, and gas. Okay, so this is the effective permeability. Today we are talking about how to measure absolute permeability, so liquid and gas permeability. So the permeability is generally defined using Darcy's law, or measured using Darcy's law, and the unit of permeability that is common in petroleum engineering is Darcy. Okay, so using this equation of Darcy, and if you have here a porous media, and you are injecting a flow, there is a flow rate, or of water, for example, passing through this porous media, and you know the cross-sectional area of this porous media, you know the length of this porous media, you know the viscosity of the brine or the fluid that you are injecting. You can measure the pressure of the inlet pressure and the exit pressure or outlet pressure. You can calculate the permeability using Darcy's law. Okay, so this is the permeability. Also, you have to know that the inlet pressure is all the time higher than the exit pressure. Okay, so this pressure is higher than this pressure. Okay, the unit of permeability coming out from this equation, if you using this equation, the unit of permeability is meter square. Okay, but it is not common. You have to convert it to Darcy or milli-Darcy. Okay? So 1 Darcy equals 10 to the power of minus 12 meter square. So for the liquid permeability, it is following Darcy's law, and you can use either brine or oil to inject. The setup using liquid permeability to measure liquid permeability, as you can see, this is a sketch, and this is the actual setup. So what happened here? You have a pump, you have a high pressure pump, constant flow injection pump. Okay, so you are injecting the pump, the liquid at using a constant flow. So you can adjust the flow using this pump, like so inject water at 0.5 milliliter, inject water at 1 milliliter per minute. So you can identify the flow rate that you want the brine or the oil to be injected inside the core. You have here a pressure transmitter or transducer. You have here a core holder. So for this core holder, you can, this is placed where your core or core plug are placed. So inside this core holder, this is a Hassler type core holder. And in the next slide, I will show you the composition of this core holder. So you have to apply also confining pressure. You will use high pressure, constant pressure pump, okay? So you can adjust the pressure. So there should be a pressure difference between the core or the pressure in the core and the confining pressure of 400 psi. Other pressure transmitter to measure the pressure difference. So this is pressure transmitter, and you can install a pressure transmitter here. And at the end, there is a back pressure regulator where you can govern how the delta P. So you can close this valve a little. If you close it like somehow smaller, little, you will get a high pressure here, and you cause your system to have a pressure built up. So you can adjust the pressure of the system here, and you have to maintain a pressure, certain pressure and certain pressure difference. This is controlled through a back pressure regulator. So the first step in any liquid on a liquid permeability is to put your core plug inside the core holder. So what is the composition of this core holder? I will try to open the camera now, and hopefully it will work. No, it's not working.
Dr. Rahabi, you should find an icon for start video.
It's not here. I cannot find it. Maybe it's
Besides
It's on Zoom video, Zoom window. So open Zoom window, you'll find the start video.
no, it's not working. All the Zoom icons are disappearing now. There is no Zoom icons or no Zoom frame. The Zoom frame is not available. I think that's it. Okay, so I will continue. You will. Okay. I'm sorry for this. So what is meant by, so I told you to start liquid permeability, we have to place this core inside a core holder. What is meant by core holder? This is like a container that you will place your core inside. So you have your core here, So the cylindrical type core is inserted inside a Viton sleeve. It is a cylindrical type hollow tube, okay, rubber, okay. So it is like I was giving you, like I was going to show you some an analog of this Viton sleeve, but I cannot open the camera. So what happened here is that you place your core, the cylindrical type core, inside a hollow tube of Viton sleeve, okay, and then you place here a distribution plug, in the other side a distribution plug, and you close everything, the empty cap and everything, you close it. So what happened here, that there is this distribution plug is like the shape here. The shape of distribution plug is not exactly like this photo, but it's the only photo that I can get for distribution plug. So it is containing a port, okay, a hole where you can inject the fluid through it to the core, okay. So this can be one hole, two holes, three holes, whatever the number of holes that you want. So up to three, it cannot be more than three. So from one hole, two hole, or three holes. So you can inject the fluid that you want. For the distribution plug here, there is a grooves. Okay, this groove will make sure that you completely nicely distribute the fluid through this core. You don't want, if there is only one port, there is no distribution. What will happen here is the fluid will leave some of the pore, not invading all the pore or all the core. Okay, so some of it will go like this, and maybe some like this. So some of the space inside this core volume will not be invaded by brine or liquid. Okay, so this distribution, the function of distribution plug is is an injection port, and to nicely distribute this fluid that you are injecting through the core. Okay. So what is the purpose of the Viton sleeve, the hollow rubber cylinder? So the purpose here that we want to inject from the liquid from one side to the other side. We don't want radical flow. We don't want the flow to the liquid that we are injecting to going radically here. So what will happen here is that we inject other fluid here that will compress this core plug. It will fill the annular space here and here, okay, and it will compress the core. So it will prevent any at higher pressure. So this pressure, for example, you are working at 100 psi, and this pressure is higher, it will be 500 psi. Okay, so according to this pressure difference, the fluid will not go through this diagonal, okay, radically, will not flow radically, okay. So it will flow only from one side to the other side. Okay, so you now understand that the core holder is a way that we can make the fluid that we are injecting going from one side to the other side without any radical flow, and the confining pressure is a radical pressure. So it is radically compressing the core without not allowing any flow through the through other than the both end of the core. Okay. So this pressure, you have no cannot exceed this pressure difference higher than 400 psi. If you increase this confining pressure higher than 400 or maximum 500 psi, you will get your core to be compressed. Okay, and you will change the pore volume. You will change the structure of the core, and you can end up breaking your core. So this core holder is important because you can use it in many experiments in petroleum engineering, like gas and liquid permeability. You will use a Hassler type. The most commonly used core holder is Hassler type core holder. The formation damage, you can use a core holder. Porosity, relative permeability, enhanced oil recovery, and resistivity. Many experimental work in petroleum engineering, you use the core holder and Hassler type core holder. So just in a quick steps, how we can measure liquid permeability in the lab. You first load your core inside the core holder, and I showed you how the core holder works. Then you will apply confining pressure using the constant pressure pump, and then you will apply vacuum. The purpose of vacuum, you want to get rid of any air inside the pore volume of the core and inside the flow line. This vacuum takes time because it's not 24 hours is high, but you can high value, but you can leave it overnight. So this is what we was practicing before. We leave under the core under vacuum for 24 for overnight. So you have to prepare your brine. To prepare your brine, you cannot. You have to use deaerated brine. Okay. So if you are using brine as the fluid to calculate the liquid permeability, you have to use brine, not distilled water. Okay. You don't want to damage your clay or your core plug. Okay. So if you used just I'm sorry, distilled water, what will happen to the clay? The clay will swell. Okay. So you don't want the clay to swell. You don't want your to damage your core plug. It is a valuable thing, and you have to preserve it. So you will use brine, so which is a distilled water, adding salt that you want, NaCl, KCl, okay, whatever combination of salts you are going to use, and then deaerate it. Okay. So why deaerate it? Because in normal, water contains dissolved air inside. And this air, if you inject it under like brine without any deaeration, the air will separate and cause a small air pocket inside the core, which will affect your permeability measurement. This is possible, and this can happen. So what you will do is deaerate this brine using a vacuum oven. I showed you before, the vacuum oven. For 1 hour, don't increase more than 1 hour or 2 hours, because you don't want your water to evaporate. Okay. So for this brine, you will use the constant flow injection pump to inject your brine. So you have your brine, you prepared your brine. It is HPLC type, not peristaltic pump. Okay. So you will choose the setting of the flow, 0.5 milliliter per minute, and then you will start injection. You will continue injection for 2 pore volumes. What's meant by 2 pore volumes? If you measure the porosity or the pore volume of the core to be 20 milliliter, so you have to inject 40 milliliter at least of a deaerated brine inside this core before taking any measurement of permeability. Okay. So, and you can adjust the back pressure. So you can adjust the pressure of your system using a back pressure regulator. This is the type of back pressure regulator. This is a high pressure, actually, taking from 3000 psi to atmospheric. But it's not necessary to use a high pressure regulator. So now you can you will allow your setup to stabilize. You injected 2 pore volume. You get the reading of the flow, the drop in the pressure, and you will arrange Darcy law. You will apply Darcy law. We arrange Darcy law to be. It is a linear function. Okay. So what we'll do here is you will plot this the flow rate over the cross-sectional area on the y-axis, and then you will plot this pressure gradient on the x-axis. And in your experiment, you will do 3 or 4 measurements at least. So you will change the flow of like 0.5 milliliter per minute, and then the liquid flow to be 1 milliliter per minute, the liquid flow 1.5 milliliter per minute. So you will change the flow and then inject the 2 pore volume at least, and then you will allow your system to stabilize, get the measurement of the pressure in and pressure out, or the pressure gradient, pressure difference, and then you will get your the points you have should form a straight line passing through the origin. The slope of this straight line is permeability over the viscosity. So if you know the viscosity of this brine, and if you measure this, I will not. It will be discussed later in the next session. But I you have how to measure the viscosity. It is a dynamic viscosity. So so permeability over the viscosity. We have the slope of this line here, so you can calculate the permeability. Practicing. Okay. If you decide that you have a setup and you want to measure liquid permeability of oil, you will use oil to measure liquid permeability. And you have you measure using vernier caliper the dimension of your core plug to be the dimension to be 5 centimeter in diameter, and the length was 10 centimeter. Okay. The viscosity of your oil was known, 1.6 centipores. Okay, the centipores is equal to Pascal second. After running your setup, you recorded a table. So here, using this pump, you set up the flow to 4.5 milliliter per minute and you measure the pressure. You set up the flow to 9.2 milliliter and you monitor the pressure. 13 milliliter and you monitor the pressure. So you have this table, okay, using your setup. Okay, this is actually what is happening in the lab. So now calculate the oil permeability. So how can we calculate this oil permeability? Again, so it is a Darcy's law. This is a linear function. You will have to plot this, but you can plot Q over A on the y-axis, the pressure gauge on the x-axis, and through the slope you can get the permeability. But you have to adjust this given. So now the first thing here is to calculate A, the cross-sectional area. So the cross-sectional area of this cool plug. So you have the flow rate adjusted, the pressure and the inlet and the pressure exit. So you have to calculate the area first. Okay, the cross-sectional area. You have the diameter, you have the length. Okay, so you can calculate the area. You don't want the length in the area, whatever. So then after you get the measurement of area or the calculate the area, so you divide Q over A and you get to put it in this column. Then you will calculate the pressure difference here. Inlet, takeaway exit, it will be delta P. Okay. Then divided by length and in the other column. You will draw this line versus the in this so in the y-axis and this in the x-axis, and you will find a line passing through the origin, and you can get the slope of this line. You are given the oil viscosity, so you can calculate the oil permeability. Okay. So I want to point something here. It's important, really. So if you look at the exit pressure, it is 0. So how can the exit pressure be 0? It is how come it is 0 atmosphere? Because it is a gauge pressure. You are using gauge pressure. Okay. So for gauge pressure, the atmospheric pressure is 0, and the vacuum is minus 1. For absolute pressure, the atmospheric pressure is 1 atmosphere, and the vacuum is 0. Do we have to use absolute or gauge pressure here to make a difference? In this case, it will not make a difference, but in gas permeability, it will make a difference. Okay, so because here, if you take, you will convert this from gauge to absolute, and you convert this from gauge to absolute, and they will cancel. So the difference between the absolute and the difference between the gauge pressure is the same. Okay, so for this you can work fine with using gauge pressure for liquid permeability. So now to gas permeability. So gas permeability, actually the gas behavior is different because gas is compressible gas. So what will happen here? We have a higher pressure at the inlet and lower pressure at the exit. So what will happen is that there will be expansion, volumetric expansion of the gas. So the flow rate through the core is not constant. And using Darcy law, we have to use, instead of the flow rate, the normal flow rate, we have to use the average flow rate or the mean flow rate. So the mean flow rate is calculated using Boyle's law. If you know Boyle's law, I told you that we used it before in using porosity. So what will happen here? You have the mean flow rate and the mean or the average pressure, which is pressure inlet. Pressure inlet plus pressure exit over 2. So this is the average pressure or mean pressure equal to the flow rate inlet times the pressure inlet. You can use the flow rate exit and pressure exit. So, but if you use flow rate inlet, you have to use the pressure inlet. If you use a flow rate exit, you have to use the pressure exit. Okay. So you will substitute in this equation, and at the end, the gas permeability will be used. This is the form of Darcy law that will be used to measure the gas permeability. So again, this is the flow rate of the fluid. Just if you, this is inlet, and the pressure is inlet. Again, if you use the exit flow rate, you will use this pressure exit. The viscosity is the gas viscosity. This is the length of the core divided by the cross-sectional area, and this is the pressure inlet squared. Take away the pressure exit squared, and you can find the gas permeability. The setup for the gas permeability is simpler, not very complicated as a liquid permeability, because you can use, for gas permeability, you can use nitrogen or helium, but the normal fluid that is gas that is used is nitrogen. So you will use nitrogen gas, and you will have a pressure regulator here, and then a flow meter attached to this pressure regulator, then a core holder. You have a pressure transmitter and the back pressure regulator. Okay. So it is more not as complicated as the liquid permeability measurement, and the gas and you can easily measure it. So this is the simplest one. So when we start to measure permeability, we start practicing with the gas permeability. The flow meter can be installed here, and the pressure in the Darcy law will be the flow in and the pressure in, or the flow meter can be installed at the end, and the pressure will be the exit pressure and the flow exit. Okay. So a quick, you load the cone sample, you do vacuum, you inject the nitrogen inside the core, and you can adjust the pressure difference here using either back pressure regulator or the cylinder regulator here. You can change the flow rate using either this or this. Okay. So it is a straightforward measuring gas permeability, but can we use this gas permeability to relate it or to calculate the absolute liquid permeability? The answer is yes, we can do so using the Klinkenberg effect. What happened here in the Klinkenberg effect? He finds that if he increased the mean pressure, okay, so the average pressure on the core, if the average pressure increases, he finds that the relative permeability decreases. I'm sorry, the gas permeability decreases. So if he used different gases. So if you have, if you use nitrogen, for example, so if you increase the mean pressure, this is the inverse of the mean pressure. So if you increase, you go this way. So if you increase the mean pressure, what you will find that the permeability of the gas decrease. And not this only, you will find that if you use carbon dioxide, nitrogen, or hydrogen, all three gases just meet at the y-axis at the same point. Okay, and this is the liquid permeability. So why the gas is taking this effect? This is called the gas slippage phenomena. So why this phenomena is occurring? So let's see how the liquid behave. In general, once you inject liquid inside the pore volume, the tiny pore volume, what will happen here? That you will find the velocity at the mid of the pore will be the highest, but the velocity of the layer of liquid next to the wall of this pore will be 0. Okay, so the wall of this pore will be 0. The velocity here will be 0. This is for the liquid. What happened here for the gas? The gas, the velocity at the wall is not 0. It have a value. So what will happen is the permeability of the gas will be high. We will have high permeability of gas. This is because phenomena called mean free path. So the mean free path is the distance that if you have a small molecule of gas, okay, you started here, okay, and there was a collision here, and the molecule just go here, goes this distance, and there is a collision here, and this goes through this distance, and there's a collision here. So at the collision point, the velocity is 0. Okay, so what we can find, or the phenomena that we find in the gas, that the distance this molecule take, okay, move between one collision and the other. Okay, so there is a collision here, and the molecule moves this distance, and there is another collision here. So this distance is the free path or mean free path. Okay, So this mean free path here, the length of this mean free path is higher than the pore volume. The pore, I'm sorry, not the pore volume, the radius of the pore, or the pore space available. So what will happen? The layer of gas neighboring to this to the wall of the pore will be at a higher velocity here. Okay, because imagine there is a collision here and there is a collision here, the velocity will be zero. So what happening here is that the velocity at the wall of the pore is not zero, because the mean free path between the collision is higher than the diameter of the pore. So imagine if you have a gas and you increase the pressure of this gas on this gas, what will happen? The molecules will be coming together, so the distance between any two collisions will be shorter. Okay, so if you increase the pressure more, the density, the length, I'm sorry, between these two collisions will be shorter and shorter and shorter until it is behaving like a liquid. And this distance will be the same as the pore one. Okay? And this is actually what is happening here in the Klinkenberg permeability. Once you increase pressure until you reach infinite pressure, infinity pressure, the highest pressure possible, what will happen? The gas molecule will be nearing to each other until it behaves like a liquid. And this is what Klinkenberg found. So, and there is an equation, okay, driven by Klinkenberg, you will find that it is a linear relation. So if you draw the permeability of gas on the y-axis and you draw the inverse of the mean pressure, the inverse of the average pressure, I don't want you to, so mean pressure is the pressure inlet plus the pressure exit over 2. So the inverse of this pressure, you will draw on the x-axis. The intersection of this line will be the liquid permeability, or it's analog to the liquid permeability, Klinkenberg permeability. And the slope of this line, if you divided it by the permeability, the slope of this line, if you divide it by liquid permeability, it is the slippage factor. In the lab, to do the Klinkenberg effect, we have to measure 2 or 3 or 4 at different mean pressure, at different average pressure. So we control this pressure through the back pressure regulator and or the cylinder. So the pressure regulator of the cylinder. So exercise. I know it's now not running late. I know. So well, the exercise now we have a setup for gas permeability. We have the diameter of the core is 3.8, the length is 7 centimeter, the nitrogen viscosity was 0.0176 centimeter, and I want you get this measurement. So you change the back pressure regulator, and you change the amount of nitrogen coming out. So you change the flow rate. You measure the pressure in, pressure out, and you get this line. So you enter the lab and you get this measurement. What you will do with this measurement? Okay. So you have nitrogen. Can you calculate nitrogen permeability? Can you calculate Klinkenberg permeability? Or can you calculate the gas slippage factor? So this is what we are going to do. We want first to start with how to calculate nitrogen permeability. So we will use this equation, okay, for gas, if you remember. But we are given because the pressure transmitter and pressure transducer and almost all the pumps actually is measuring gauge pressure. I told you in the liquid permeability, it doesn't differ if it is a gauge pressure or absolute pressure. But in the case of the gas, it is different. Okay, so you have to convert this gauge pressure to absolute pressure. Okay, so what you will do is, because this is PSRG, you will convert it to PSIA, which is the absolute pressure. You will add 14.7. So for this column, you will add 14.7. For this column, you will add 14.7, and you will get a new pressure and inlet and exit. For this equation, the units of pressure should be atmosphere or Pascal. Okay, you have to convert the atmosphere to Pascal at the end, but you can work with atmosphere and Pascal. Okay, So for the atmospheric pressure, you have to divide by 14.7 for this column. 14.7, you will divide each value in this column by 14.7, and this is the column. This you have to divide each value in this column divided by 14.7, and you will then you will have to do this term, and then you get the flow rate. You will adjust the flow rate and divide it by the area, cross-sectional area. Already you know the diameter, so you can calculate the cross-sectional area. So it is, I'm sorry, centimeter cube square, centimeter square. I calculated it incorrectly. Okay, so so you have here divide Q. You will you will transfer this this flow rate to centimeter cube per second or meter cube per second, because you have to transfer all the unit to meter and the pressure to Pascal. Okay. At the end, you will get the permeability, gas permeability using Darcy in the unit of Darcy, and you can convert it to milli-Darcy, and you can calculate from each value the average and the gas permeability. You get the nitrogen gas permeability. So what about Klinkenberg effect? What permeability? What we can do here is we have the initial pressure and the exit pressure. We can calculate the inverse of the mean pressure, which is the mean pressure P initial pressure plus the exit pressure over 2, and then we inverse it, so we get this column. We already have the permeability from the other, so this is the other permeability here that we get here, this and this. Okay, so we can draw the permeability on the x-axis and the inverse of the ampere of the mean pressure on the y. I'm sorry, on the y it's x-axis, and the permeability on the y-axis, and you will extend a line. You will draw it and extend the line to meet at 0, and you will find intersection here. It will be the liquid permeability or Klinkenberg permeability. The slope of this line, okay, the slope of this line is equal to, okay, will be the slippage effect times the liquid permeability. So if you get the slope and divided it by the liquid permeability, you will get the slippage effect, a slippage factor. Okay. So the last thing for this lecture for today, I know it is long, but hopefully you are enjoying it. So for the how to measure the contact angle and the interfacial tension. So the contact angle is an important measurement, and the interfacial tension, it's affecting really the capillary pressure, the relative permeability. Interfacial tension is affecting the wettability itself. So it's an important value to measure. So as you can see from the equation of capillary pressure, the interfacial tension and contact angle is really governing the capillary pressure. And for the adhesion force, the interfacial tension and the contact angle governing the adhesion force. So the contact angle in general is an important measurement, and it is an indication of wettability. So we can define the wettability of the tendency of one fluid to spread over a solid surface, okay, in a presence of second fluid. So if you have a rock surface and the media was oil, and you place a water drop on and this surface was water wet, what will happen? What will happen that the water drop will spread, okay, because the attraction force here or the is very low, okay. So the water can spread and displace this oil. What we can find here is the contact angle. What is the contact angle that we'll find? It will be less than 90 degrees because it is a water wet surface. So the water will spread and form a contact angle between oil, water, and sand here, or whatever, or the core surface or the rock surface, okay, to be 90 degrees. So how we can measure the contact angle? I want to point this out. So this is the surface, okay, the contact between the water and the rock surface and oil. So you draw a tangent to the interface between the water and the oil. So the interface between the water and oil, will draw a tangent to it, and then you will measure this contact angle through the denser phase. So which one is higher density, oil or water? Water. So you will measure the contact angle through the denser phase. This is a water-wet surface. Okay. Contact angle was lower than 90 degrees, okay, and the water spread. So what will happen if it was a oil-wet surface? The attraction force or the adhesion force between the water and surface is weak, so the oil cannot spread. Okay, and there will be like a contact angle between the water and the oil and sand to be of higher than 90 degrees. Okay, no tendency for the oil to spread. It will be water repellent. It will repel water. So this is an oil wet surface. What about neutral wet? What is a neutral wet? Intermediate. I'm sorry, intermediate wet. So intermediate wet is it doesn't have a tendency to water or oil. The preference for water or oil are the same for this surface. So you will find the contact angle is nearly 90 degrees. Okay. So this is meant by intermediate wet. What we can find on in an oil reservoir, it is all of this type. You can find water wet type rocks. So what are meant by water wet oil rock? So what you can find, if the rock was water wet, as you can see in here, this is supercritical CO2 and water. I showed you this photo before, but if you have a look on this, you will find the tiny small pores to be occupied by water, because this is a water wet surface. So the water will be able to invade the very small pores. And also, if you have a look on the surface, you will find the water forming a small layer, a thin layer on the sandstone. So it will be covering this sandstone this core. Okay. So the grain of this rock will be covered with water, because the water has a tendency to spread, and the oil or the supercritical CO2, because they are the same, they having the same behavior. So it will be occupying the bigger pore and in the middle of the pore. So you can see here, water are spreading over the grains of the core, and the oil is in the middle, or the supercritical CO2 is in the middle. Okay, this is a water wet. The contact angle, if you measure it on the surface, it will be lower than 90 degrees. For the oil wet sandstone or whatever carbonates, you will find that the oil in the reverse, it will be occupying, if it is oil wet, the oil will occupy the tiny small pores, and the water will fill the bigger pores, and it will be in the middle of the pore. Intermediate wet, it will be, I showed this before. So for what is meant by fractional wet, it's a mixed wet. So you have water wet minerals, and after some distance in the reservoir or the oil field, you will have an oil wet mineral. So I find this interesting photo of environmental scanning electron microscope. So if you see, look further, so this is a reference of the photo. So this is a quartz, okay, quartz, and this is water drop, and the media here is oil. The medium here is oil. So if you look here, if you draw the contact between the water and oil and the quartz and oil, if you draw a tangent here, and this is the contact, you will find a small contact angle. It is less than 90 degrees. Okay. So just 20 micrometer apart from this is the clay, and this is the water drop suspended in or in contact with the oil. So it is nice ball. It is oil wet. So this is water wet surface. The oil is spreading, but this is an oil wet surface after just 2 micrometers. So you can find mixed wet in a reservoir, in an oil reservoir. So how can we measure this contact angle in the lab and the interfacial tension? There is many methods, and one of them is Amod test, but really the time was very tight, so I will not go discuss Amod test, but this is one of the tests that you have to look at and read. So the contact angle and interfacial tension, I will discuss the optical tensiometer. So for the contact angle, we use Cecil drop method, and for the interfacial tension, we use pendant drop. So starting with a Cecil drop, so you have a surface, you put like a drop of the water on this surface. Either the media here will be oil, or the media here, medium here will be air, whatever you want, and no change in the just a photo shot here, and you measure the contact angle. So the contact angle here, as you can, this is the interface, this is the tangent between the water and the oil, and you measure through the denser phase. So the contact angle here is 122. This was air. Okay, so air and water drop, and you will find that this surface is oil wet surface. So this is called static contact angle. So sometimes falsely it is called it's called dynamic contact angle. You have to differentiate between dynamic contact angle changing of the contact angle changing with the time, and the receding and advancing contact angle, which is the contact angle hysteresis. So the dynamic contact angle here is the changing of contact angle with time. So using also the same device, you can monitor the change of the contact angle with time. Sometimes if you draw the contact angle here and the time of exposure to air, you will find here sun is stabilizing and then increasing. Okay? So this is one of the measurements that you can do. Receding and advancing contact angle is actually what is happening in the reservoir when it is different. If you are doing primary drainage or imbibition, secondary imbibition, it's different if the non-wetting phase or the supercritical CO2 or the water is or the oil is displacing the water, or the water is displacing the oil. In the case that oil was displacing the water, so if the here supercritical CO2 or the oil was displacing the brine here, this is a primary drainage, and the contact angle here is a small, and it is called receding contact angle. So if the brine was displacing the supercritical CO2 or is displacing oil, this is called secondary imbibition, and the contact angle in this case is called the advanced contact angle. If they are not equal, they are not the same, and you have to do some. Sometimes you want to know the history, the contact angle hysteresis, which is the advanced contact angle take away the receding contact angle. Using the optical tensiometer, you can measure this through tilting the surface. I will not show it. I will not go in detail, but if you tilted the surface of that you will put the, your sample in until just the drop is like just moving, and you will get the contact angle advancing and receding together. Or the other type here is that you introduce a water drop and the volume will increase, and so I don't want to go through some very complicated, but this is so if you have the contact line here and you introduce the volume of the water, the contact angle will increase, but the contact line here is constant. Then once you are introducing more and more water inside it, you will find that the contact line is starting to increase while the contact angle is the same. This is the advancing contact angle. If you start the same and withdraw the water, so you can get the receding contact angle. Okay. So if you have water and oil together, okay, if the water was opaque, okay, it's not transparent. If the I'm sorry, if the oil was opaque, not transparent, and how can you put a drop of water on top of this on the top of the rock surface? How? You will not, it is optical tensiometer, so it is depending on the light passing through the transparent or nearly translucent surface. You can work with translucent surface, medium. So what will happen here, you have to place a drop of oil in the water, but for normal surface, if this surface was down here in the bottom, and you place the water on the surface in an oil medium, what will happen during because I'm sorry, if you have a surface and you place the medium here was water, and you place an oil drop, because of the buoyant force, the oil will go to the top. So what we do here is we do a reverse thistle drop. So we have the rock surface here. This is the water medium here, and we place the oil drop using a hooked needle at the bottom of the surface. Okay. And we measure the contact angle through the denser phase. So the denser phase here, so you have the oil drop, and the denser phase is you will measure the contact angle through the water, because this is the water, this is the oil. You cannot place in you cannot use sisal drop, normal sisal drop, because the oil drop will go to the top, will float. So this is one of the measurements that you can get. Interfacial tension, you will use, you can measure surface tension and the interfacial tension using bend and drop. What is the bend and drop? You place a drop of water or whatever the fluid that you want. If the surrounding medium was air, okay, this in this case is a surface tension. Okay. So you can measure the surface tension. That's a 5 microliter from 5 to 10 microliter drop, and you can measure the surface tension. If the surrounding media was other liquid like water in oil, or oil in the medium was water, then in this case it is interfacial tension. As you can see here, I would like to also to look here that it is like a teardrop. So it should be like a teardrop. It cannot be a ball. The correlation here will be wrong. So in this device, you can see this is a aquavit containing water, and there is a drop of oil, small drop of oil injected in it. And you want to measure the interfacial tension. If you look at the software here, you will find the oil drop is like a ball. Okay. In this case, you cannot use a normal bend and drop, but you can use normal bend and drop if this was oil and this is water. Okay, if this was water and this was oil, as this case, you cannot use normal bend and drop, because because of the buoyant force, the oil drop will not be of a tear shape. It will be of a spherical shape. So this is why we get reverse bended drop. So it is a hooked needle. So this is the hook, okay, attached to a needle, and then we place. This is the water. Actually, this is a nanosilica. Okay. Okay. This is opaque, relatively opaque, and you have oil drop here, and it is like tear-shaped drop. You can measure the interfacial tension. The last point here is the high pressure measurement. Sometimes you need to do your contact angle interfacial measurement at high pressure, and this can be done through using a high pressure chamber. This is a chamber containing three windows. This is the camera, and this is the light. The light goes through this and the camera receive or videotape or photo what is happening inside this chamber. And this chamber is to look or to investigate what is happening. The pressure here can be up to 400 psi and temperature 200 degrees Celsius. And actually, if you want to measure actually what is happening at the condition of the reservoir. Reservoir condition can be conducted using optical tensiometer, but with a special cell for high pressure cell. If you want, you can place a tiny small rock surface inside and do contact angle, or you can just do bend and drop using this injection board. Thank you, and hope that you did enjoy this lecture. It is a long lecture, but I'm sorry for this long time.